Swayam Prabha. Digital India. Educated India.
See, in 3D kinematics, one of the important concepts that you learn is fixed point rotation, which we have seen in detail in the previous class. You know, in two-dimensional analysis, we have looked at a non-rotating translating axis attached to the body, and we also saw a rotating axis attached to the body. We will now extend it for three-dimensional problems. So, we move on to general motion, and I am not calling this as plane motion. So, it can be any motion in space, and I have a three-dimensional body. This body has some angular velocity and some angular acceleration. We have never put any restriction on this. And what you need to notice is these could be of different orientations in a three-dimensional problem. Similar to what we have done in 2 dimensions, choose a point B as the origin of a translating reference system. It is a non-rotating reference axis. So, choose a point B and attach small x, small y and small z to this point. And we have already discussed in detail, if I attach a non-rotating axis, what way the person would perceive in a two-dimensional system. In a two-dimensional system, we said that he would perceive that it is rotating in a circular fashion. Here you are talking in terms of 3 dimensions. Here also the object will rotate about point B. Instead of a circle, you would see that as a sphere, because we are looking at 3 dimensions, that is only difference. So, similar to the earlier one, we put the position vector r b, position vector r a, and we are considering a rigid body. So, the distance between points B and A remains fixed, and that is given as the position vector r, or you can also qualify it that as position vector r a with respect to B. So, the main difference is point A appears to lie on a spherical surface with B as the center. So, that is the only difference between a 2-dimensional analysis and a 3-dimensional analysis. So, the important concept is, if you sit on a body and translate with it, you would see that it is rotating. And no matter whether I see from point A or point B, I would still perceive same rotation. There is no change in that. Whatever we have discussed in 2 dimension naturally extends here. All the vectors will have 3 components. Instead of a circular motion, it will have the point A would lie in a spherical surface. This we have also discussed in detail in 2-dimensional analysis. Whichever point I take, I will still have the sense of rotation preserved. Sense of rotation does not change. Okay. And it is a very subtle concept. Whatever we have discussed in 2 dimension, you can say extend it for 3 dimensions. And whatever the expressions that we have developed, we had V A as V B plus V A with respect to B, and the expressions what we have learned for circular motion again applies. Here the vectors have 3 components, and omega is the instantaneous angular velocity of the body, and r is the position vector r of A with respect to B. So, similarly, you can also write for the acceleration, and here again I can write comfortably the relative quantity as consisting of a normal component and a tangential component. Here again you use equations developed for simple circular motion. Only thing is the components are having the vectors will have 3 components in x, y, z, and you have to do little more computation when you do the mathematical part of it. So, I have the normal acceleration as omega cross r and tangential acceleration as alpha cross r. So, whatever you learn as circular motion used in different ways at different parts of the course, the basic equations remain the same. You use it appropriately depending on the context. So, I am in a position to find out the velocity as well as acceleration. Now, we move on to rotating axis. So, here I have a axis like this to emphasize that this is not a translating axis. I show that it is having a rotation. All the symbols are very similar, there is no difference in the symbols, and here again you have this unit vectors, and unit vectors we will write it as I and j later. And instead of looking at like this, if you look at as product of omega cross the position vector, then it is easy to employ and use. All these we have done in detail, so I can afford to go a little faster. So, you write the basic expression like this and write it in terms of the unit vectors. Then for convenience we replace it as I and j, and I said that I can have velocity as well as acceleration, angular velocity as well as acceleration. And whatever we have discussed, we have derived the expression for the velocity, we have also derived expression for acceleration, they remain same, and you also know I dot as omega j, which could be written differently as I dot as omega cross I and j dot as omega cross j. This kind of writing is very easy for your mathematical simplification. We have also used this when we discussed fixed point rotation. There again you will have I dot, j dot, k dot depending on which one is having this as non-zero. And in 2-dimensional analysis we have put this as omega, and I have also written down these expression in terms of omega. In 3 dimension, people also give this as a capital omega. So, I have body rotating with some angular velocity, and you have the axis rotating with an angular velocity capital omega. Just for convenience, see, we solve problems with several omegas, and I said that you should be alert in using the particular omega. It is again a notational change. There is nothing different from the conceptual point of view. So, I have a rotating reference axis attached, and you distinguish there could be some part of the 3-dimensional body will be rotating with some angular velocity. The axis angular velocity you keep it as capital omega, you reserve that as a symbol. So, it makes your life simple when you write those expressions and substitute the relevant quantities. I have the position vectors marked, and I also see I dot as omega cross I, just repeating those expressions, j dot as omega cross j, k dot as omega cross k. and you have a similar expression like what you have got in 2 dimensions. From a notational point of view, we write it as a capital omega, and each of these vectors will have 3 components. So, you have the angular velocity of the axis, and I have the angular acceleration is written down like this. So, this is the Coriolis component of acceleration, and I can also visualize, I have written it for acceleration, you can write it for velocity also. Just to emphasize, I choose my rotating reference axis, so that I am in a position to easily measure the velocity VREL, which is nothing but V x y z here, and AREL, which is nothing but A small x y z here. And on the left hand side, I have referred with respect to the fixed axis capital X y z. The difference is, in the 2 dimension we had only x y, here I have x y z, otherwise there is absolutely no change. The mathematics will be little involved, and the problem complexity can be little higher. Other than that, it is just an extension of what you have learnt in 2 dimensional analysis. I have written down this form of expression for acceleration, you can write it for velocity as well. So, when I say VREL, it is V x y z. So, let us solve some interesting problems and just observe the animation, so that you recognize what are all the motions that are available to the mechanism. So, you perceive and write them clearly in the sketch. One is, I can see that it is rotating about this vertical axis, that is very clear. So, I have a rotation about z axis. Then observe that this disc is not stationary, this is rotating which way? This is rotating anticlockwise, that is also very clear. And you know, this also has a provision, when I have this motor can be kept at any angle. There is also a provision like this for this, and you are given the capital X y z in the problem statement itself, and you are also given small x y z for the problem under consideration. So, write down the problem statement. So, the motor housing and its bracket rotate about the z axis at the constant rate of omega equal to capital omega equal to 4.5 radians per second, and you have the spin of this disc is 12 radians per second, and you are also given what is the rotating frame of reference. It has made your life simpler, it is listed in the problem statement, and this axis is located at an angle gamma. If gamma is 30 degrees, determine the velocity and acceleration of point A at the top of the disc. So, it is a straight extension of what you have done as a 2-dimensional analysis to a 3-dimensional analysis, and you could see very clearly when I have a motor, when I sit on point B, I would perceive the rotation very comfortably, and I can find out what is VREL and AREL very easily. So, even though you do not decide what is the coordinate system that you should choose, even though it is given in the problem, from the problem you can understand that you are in a position to find out AREL and VREL comfortably with this. Leaving that apart, everything is in 3 dimension, that is all the difference. Okay. So, let us get into the solution of the problem. This diagram also will be repeated again and again, so that you will have an opportunity to fill in the blanks. And one of the important aspect in this problem Because we have not done that in detail in 2 dimension, I thought I would at least solve one problem where you have a coordinate axis is inclined, and this it is better that we get the interrelationship between coordinates upfront, so that the mathematics becomes much simpler. So, the way the coordinates are aligned, this plane, that small yz plane, is actually merging with the yz plane. It is only at a height of 100 millimeter that is given in the problem. So, the x axis is small x is aligned to capital X. So, I have capital I equal to small I. I have not shown the unit vectors here. For the capital X y z, you have capital I j k, small x y z, I have small I j k. And I would like you to fill in this matrix. Do you know that you can write the small unit vectors in terms of capital J and K in a matrix fashion? Okay. Please fill in that and then check your matrix with mine. I will just show that. It is easier way of writing things. Okay. I can get small j and k from capital J and K, because what I have is the axis y and z are rotated about the x axis by an angle gamma. So, you can easily write this as a rotation matrix, cos gamma sin gamma minus sin gamma cos gamma. I can also find an interrelationship between capital J k and small j k. You can do the reverse of it also. So, you just change gamma to minus gamma, I get this expression. So, the idea is when you have axes which are displaced like this, it is better to find the interrelationship upfront before you start doing the mathematical calculation. Then you can figure out which way you would simplify the mathematics. So, then I can write, I have written what is the relation between I capital I to small I. I will follow the same trend, capital J to small j and k, capital K in terms of small j and k. And in the problem you have the rotation about the capital Z axis. So, you will have necessity to get capital K cross I and capital K cross small j, capital K cross small k. So, I also get those relationships upfront, so that I can do the mathematical simplification easily. And when I look at k cross I, small I and capital I are same. So, I get this as capital J, and capital J is j cos gamma minus k sin gamma, and I have k cross j as minus I cos gamma. So, you can do that for the k cross k. See, normally k cross k, if I say, it will be 0, but here it is capital K cross small k, fine. So, you have to be alert, you should not switch off your mind and solve the problem. That turns out to be I sin gamma. Once I have these quantities, then the problem, the solution to the problem is fairly straightforward. So, I have this coordinate angular velocity is capital omega. So, I write each term what we have done in the 2 dimension, similarly you do that. So, you write V b plus omega cross r plus V del, find out each of these quantities. V b is the coordinate velocity. So, which you can find out from the diagram easily. So, it is omega cross r b, and so this is the values in numbers. So, I have k cross j. So, k cross j becomes I. So, I can write this as minus 2.36 small I. So, essentially I am writing all these quantities in terms of the rotating frame of reference small x y z. So, I know what is V b, then I do omega cross r. So, the r is, you are given this value 450 j plus 0.180 k, and you know omega. Then you also have this interrelationships between the coordinates. So, when I use these, I get omega cross r, because I am going to have this, that is why I put what is k cross j and k cross k and so on and so forth, all that you have. So, I can easily simplify, and this turns out to be an expression like this. So, it just algebra is very similar. You have to be alert and handle the coordinate system carefully. Then we go and find out what is VREL. So, omega cross r is minus 1.35 I meters per second, and VREL you can find out based on the spin velocity. Okay. So, VREL is nothing but P cross r. So, thankfully, the problem statement itself has different symbols for omega. It makes you less burdened in solving the problem. Okay. So, I know VREL. So, when I substitute for all of these quantities, I get the velocity of point A comfortably as minus 1.55 I meters per second. So, one of the challenges in this problem has been how to handle the coordinate system. Other than that, it is simple and straightforward to handle. Similarly, we move on to acceleration. So, have a mnemonic way of remembering this expression. You have to remember this, otherwise you cannot solve any problem. And find out the coordinate acceleration. So, this is omega cross r b. We have already written down all these quantities earlier. So, I get this as 4.5 k cross 4.5 k cross 0.450 j. So, that turns out to be minus 9.11 j, and I always express the final expression in terms of the rotating frame of reference. So, I write it in terms of j and k. So, similarly, you do it for each of the terms. I have A b obtained like this. Then I have omega dot, this is having a constant angular velocity. So, omega dot is 0, and I have omega cross r. So, you have this expression, and you can simplify that quite comfortably, because we have all the interrelationships available, k cross j, and then you also need k cross k, that is also available. So, I express everything in terms of small I j k. So, you look at this interrelationship, and finally, you get omega cross r. So, it is very straightforward and simple, provided you handle the interrelationship between coordinates systematically, fine. And I have this Coriolis component, which can also be written in terms of small I j k. So, I get the final expression like this, and ARL you can write it in terms of spin velocity, and there is only constant spin velocity is given. So, it is easier to find out this. So, when I put all these quantities, I get the acceleration at point A, and we can also find out the magnitude. It turns out to be 28.28 meters per second square. So, this is a straight translation from 2 dimension to 3 dimension. Only thing is the coordinates were little difficult to handle, but you had solved a similar problem in 2 dimension also. What is the problem you solved? You solved the problem when this gamma was 90 degrees. Okay. That is the problem you solved. When I change the gamma, it looks a very complicated problem, and thankfully, I had a good animator who could make this visually possible. Okay. Then we move on to another interesting problem. It is a very interesting problem. First, observe what is the kind of motion this has. What are all the motions? Because once you understand the motions first, then you can attempt to make a solution. Let us see what are the things that you can see easily. I have this rotating about this axis, that is the simplest one to see. So, I have labeled this as omega 2, this is rotating about this axis, no difficulty at all, anti-clockwise. And what way this arm is rotating? That is also anti-clockwise. That is also easy to see, it is also rotating in anti-clockwise motion, or it is rotating in clockwise motion. Okay, you can see that it is rotating like this, okay, rotating clockwise. And look at what way this disc is rotating. This disc, what way it is rotating at this position. You have to worry only about what happens at this position. First, observe this mechanism, that is rotating clockwise. So, I have given the spin angular velocity in the symbol p. So, this is a very interesting problem. See, we have looked at when I select the rotating frame of reference, it can just rotate or it can rotate in space, which we have looked at it. Now, you have learnt in 3 dimensional kinematics, I can have fixed point rotation. So, here I am going to select my rotating frame of reference, which is also given, which is attached to the arm at the center of the disc. So, this rotating frame rotates with this arm as well as it has 2 angular velocities omega 1 and omega 2, which are perpendicular like this. So, the rotating frame of reference has the fixed point rotation now. So, you can also have that, fine, that is why I chose this problem. And if I sit on this disc here, I just see the disc simply spinning, and it is easier for me to get the B rel and A rel. So, to remove your mental block, I particularly chose this problem. A rotating frame of reference can have a very complicated motion. There is no harm in selecting an axis like this, as long as I am able to get A rel and V rel. If you understand this, rest of it is very simple. So, you have to appreciate the motions in the body. These are all fictitious problems where you get trained to look at different types of motions. See, to effect this, it will be a very difficult circus to devise a gadget to have all these motions packed in a small fashion. Okay. And you are also given the values of these velocities. The spin velocity p is given as 0.8 radians per second. Both omega 1 and omega 2 have 0.4 radians per second. So, you are asked to find out the velocity v and acceleration a of point A on the rim of the disc as it passes the position shown. And in order to have simplicity, because the problem is complex, The problem statement itself dictates what is the capital XYZ, what is the small xyz. Even if it is not given, you are sufficiently trained how to choose the rotating frame of reference. The choice is I should get ARL and VRL, I mean VARL and acceleration ARL comfortably with the quantities specified in the problem. That is possible only if I sit on this disk and move with it. Okay. Once you understand this, rest of it is straightforward. So, we have fixed point rotation. So, the angular velocity of xyz axis is, we have already seen that I can have a vectorial addition. So, I put the symbol capital omega denoting that this is the angular velocity of the rotating frame of reference. I have omega 1 and omega 2. And you should also note that all the axes, there is no confusion in the axis. That is why I chose the problem, because the problem is complex from a different perspective. I wanted to make other quantities as simple as possible, so that you get the idea behind it. So, I have this as minus omega 1 I plus omega 2 capital J, but I equal to I and j equal to j. So, I can rewrite as minus 0.4 I plus 0.4 j, and you also know how to get the acceleration. So, whatever you have learnt in fixed point rotation, those concepts you have to stretch here and then do it systematically. So, I have this disk and this is same as small x as well as capital X, and I have this capital Y axis here, and I have the small y axis here. I have the point B marked at the center of the disk, and I have the point A, and this has a spin velocity clockwise, and I can easily find out the VRL as well as ARL. So, you choose the rotating frame of reference such that you can measure these quantities or determine these quantities comfortably. And I have VB as the coordinate velocity. So, this is the position vector. I have this as BI, and B is also given, it is given as 350 millimeters. I know omega. When I say omega, I must recognize that it has combination of omega 1 and omega 2. So, I have the expression translated into numbers, and finally, I have missed some substitutions. Please verify this, verify them, and if there are any typographical error, please bring it to my attention. I get VB as minus 0.14 k meters per second. And we would also determine, when we find out VRL, we will also find out ARL, and I have to get the coordinate acceleration. So, R as BI. So, I have this as omega dot cross BI plus omega cross BI, and I should recognize that I will have omega dot, and this I can write it in terms of omega cross VB, which we have always been doing, okay, to simplify the calculations. And how do I write omega dot? Go back to your fixed point rotation. So, I have to have omega 2 cross omega. Omega 2 cross omega 1 is what I want, but I can also write it in terms of this, because this j cross j will go to 0. So, essentially I get omega 1 omega 2 k. So, you should recognize, even though these angular velocities are constant, because of the directional change, you still have capital omega dot, it is not 0. So, it is a very nice problem combining the fixed point rotation and rotating frame of reference. So, once you have solved a problem like this, then you have many recipes for you to attack a problem. So, I have this value substituted and I get this as 0.16 k radians per second square. So, all the other quantities I can put omega cross V b and so on and so forth. So, I have this as 0.056 j and I get omega cross V b, the values are substituted and this turns out to be minus 0.056 j minus 0.056 I. So, I finally get A b as minus 0.056 I meters per second square. So, I have been able to get the coordinate acceleration. Then I have this V a equal to V b plus omega cross r plus V rel, the standard expression, and V rel is simply as R p I. I can also write A rel 0.06 I meters per second and A rel is minus R p squared j. So, the choice of your rotating frame of reference is selected so that you comfortably evaluate V rel and A rel without any difficulty. But I can have a very complicated motion of the rotating frame of reference. It has a fixed point rotation this time. And you can write what is R, it is given in the problem statement, what is the size. So, I can get omega cross R and substitute these values. I get this as minus 0.03 k meters per second. So, I have V a as in terms of expressions. When I substitute the values, I have this as 0.06 I minus 0.17 k meters per second. I have missed some steps, please fill in those blanks, substitute and then verify that the final expression is correct. So, we have been able to find out what is V a. In a similar fashion, we will also find out the acceleration. You have to recognize that the rotating frame of reference can have fixed point rotation. There is no mental block in selecting that kind of a axis of reference. That is the message in this problem. So, I have this expression for acceleration and I know what is R, which is 0.075 j, and we have already determined what is A b, and we have also determined what is omega dot, and when I put omega dot cross R, I can get the value like this minus 0.012, and I have omega expression is also given. So, I can write what is omega cross R. Omega cross R is this quantity. Omega cross R turns out to be like this. Then I can also write, we know what is V rel, we know what is A rel, V rel is so much, and A rel also we have determined it earlier. So, I have all these quantities. So, I can easily compute 2 omega cross B rel as well as put the value for A rel. So, 2 omega cross B rel turns out to be minus 0.048 k. So, when I put all these quantities, I get the acceleration finally as minus 0.08 I minus 0.06 j minus 0.048 k meters per second square. So, it is a very nice problem which combines rotating frame of reference and fixed point rotation. And if you are systematic, there is no difficulty in solving this problem. It is fairly straightforward, but you have to be extremely systematic, like what I have shown intermediate steps. If you develop this kind of a habit, it is also easy for us to grade your paper, rather than you write the final expression with, if the final expression is correct, there is no difficulty. If there are mistakes, how to give partial marks? It becomes so difficult for us to do that. Okay. So, in this class what we have looked at is extension of problems in 3 dimensions. We have looked at non-rotating translating axis attached to the 3-dimensional body, then a rotating frame of reference attached to the 3-dimensional body. First we solved a simple problem where there was the axis were little difficult to handle. So, we have also learned how to handle those interrelationships comfortably. Then we looked at another very interesting problem wherein we combined fixed point rotation and rotating frame of reference. The rotating frame of reference can in general have even fixed point rotation. There is no necessity that it should be a simpler axis. It can have a complicated rotation. Thank you.